Okay? So when we have a first order linear, that's from the last class, that's where we use the integrating factor. So dv dx plus some function of x times v to the first equals some function involving only x. It's linear in v. And what would be our integrating factor?
E to the integral of negative 1 over
E to the negative 1 over x. Yeah, natural log x would be x to the negative 1, I think, after they finish with that. Okay? All right. 1 hour and 1.5, is that right? Okay, so should we finish that one off? Well, I'm going to leave it there because we've transformed this into a different type of equation using that integrating factor. Then you use that method, multiply both sides of the equation by that linear factor, solve for v. And then once you've solved that for v, you can go ahead and replace v with y to the negative 2. Y cubed. Y to the 1 minus negative 2. So what I'm going to do is say what we get. Y cubed would be equal to x to the 4th plus cx. Okay. So that's going to be part of just the homework over the weekend. Once we get to that integrating factor, you can solve that for v. Once you solve it for v, well, you replace v with y to the, it was 1 minus n, and n was negative 2, so v equals y cubed. That's where this came from. So check that that's right as a general solution. Okay? All right. One more example, and then we're going to might as well take a break first. And the last part of 1.6 is the discussion on reducible second order. Oops, DEs, differential equations. Okay, and reducible means it can be, well, what we've done till now is substitutions that transform the differential equation. This is a big picture thing. It transforms the differential equation into something we can work with, either separable or linear. A reducible second order differential equation. It takes a second order DE and somehow transform it so it turns into a first order and solve that, and then integrate to find the solution curve. All right. And this will work when either the dependent or the independent variable is missing completely. So when it's completely, that's an L, completely missing from the equation. Okay. So as an example of a reducible, something that's missing, x, y double prime equals y prime. Now you might be thinking, wait, but there's both y and x here. Well, there's x, but there's no y. There's only y prime and y double prime. Okay, so the dependent variable represents y. It's missing from that equation altogether. Okay. So just call that equation 1. We're going to come back to that. So y is missing. All right. So there's a second order different derivative of y? There's a first order, but there's not a y. So we can make a substitution for a second. Let p represent the first derivative. Okay? So we're equating some variable to the first derivative. Now, p prime with respect to x, so derivative of p with respect to x would be what? Well, derivative of p, well, p is the first derivative. So this is literally derivative with respect to x of dy dx. And the notation we use for a second derivative like this, d squared y, because you see two d's right back to back, dx squared. Okay? So now, this is like our y double prime. And oops, dp dx. dp dx is like p prime, right? Yeah, that's just p prime. So substituting this into equation 1, y double prime is just p prime, right? So y double prime is the same as dp dx equals y prime, and y prime is just p. So that's what it's meant by reducible, by making this assignment that this variable, dependent variable p, represents the first derivative of something already. So that's p, and then this just represents p prime. Okay, so we've transformed it into, it's just the first derivative of p with respect to x. All right, now it's separable. If I multiply both sides by dx, and divide by p, divide by x, we get dp over p equals dx over x. Okay, and then we can integrate both sides of that. All right. So, on one hand, we got natural log p. Equals natural log x plus c. All right. So applying the exponential function to both sides, right, to get that p out of there, we get absolute value p equals e to the natural log x, that would be x, times e to the c, right? And if I call that for a second just c1 absolute x, I'm just going to assume that, yeah, here it is, x is greater than 0. So we'd have p equals c1x. And at this point, if we don't know if p is positive or negative, we drop this and say, okay, p equals c2x, where c2 is positive or negative. It could be anything. In this case, e to the c, if I call that c1, that's a positive constant. Okay? But if I drop the absolute values on that side and call it c2, well, c2 represents plus or minus c1. It could be anything. Positive or negative constant. Okay, which would be determined by any initial condition that you would get. Now, that's solved for p. And what does p represent? dy dx. Right. All right. dy dx equals c2x. So if we integrate that, then we get y. Integrate that with respect to x. So y would be c2x squared over 2 plus some other, call it c3. Okay. What's that? Oh yeah, this is, I'm integrating with respect to x. X squared over 2 plus some other arbitrary constant. Yeah. X squared over 2, so you get c2 over 2x squared plus some other arbitrary constant. I'm just not getting for c or d for the constant. Okay, so reducible means with a substitution of like p equals dy dx or something like that, then you can work backwards from there to solve for p, and then once you know p is equal to dy dx, one more equation. All right, let's take a short break. We're going to come back. I got some practice, a little bit of practice problems that I'm going to give out to you, a little activity. Well, let's take about 8 minutes. So 2:52.